Hi, my name is Lexi, and I'll be going over the solutions to the Module 3 practice problems. So for the first problem, we have 583 female workers in the 2012 GSS were asked how many hours they worked in the previous week. And then we have our mean hours and our standard deviation, and we want to know if the population mean work week for females is significantly different from 40 hours. So first, as always, we need to make our hypotheses. So we'll first have our null hypothesis, which will be H0, and that will be that our population mean is equal to 40. And our alternate hypothesis, HA or H1, is that our population mean is not equal to 40. And since they don't give us an alpha value, we can assume that our significance level is 0.05, since that's commonly used. And then we don't have our population standard deviation, but because our sample size is so large, we can safely use the z-test since our distribution should be normally distributed. And so we can use, so first we can get our values. So we have our population, our sample size is n, so that's 583, and then we have our sample mean, which is x bar, and then we have our sample standard deviation, which is s, and we can plug them into our z formula over here that I have to the side. So we can write that out. So we have z is x bar, so 37 minus 40 divided by, and again, since our sample size is so large, we can use our sample standard deviation as an estimator for our population standard deviation. So we can use S here, and that's 15.1. And then we can use our square root of our sample size, 583. And that should come out to negative 4.7971. And now we can pull this up on our z table that I have here. So this is your formula sheet. So you can use this during your exam. So we have our z table here, which will show our area under our normal curve, and then we'll look for our value. And note that since our formula says that we can use, for our p-value, when we have a two-tailed test, we can have 2 times the probability of z being greater than the absolute value of our test statistic. So the absolute value would be 4.7971, and then we can find that here. And we see that the greatest our table goes to is 3.4. So our value is way higher, so it means it's way past this end over here, which means the area to the right, so our tail, is going to be so small that it'll be really close to 0. So we can say that our value here is really close to 0, and then we can compare our p-value So our p-value, which is around 0, is less than our alpha value, our significance level, which is 0.05. And since it's less than that, we can reject our null hypothesis. And so we can say that we have significant evidence that the population mean work week for females is significantly different from 40 hours. Okay. For our next problem, we have an experiment on chlorophyll, and we're trying to find if the ratio of green to yellow of these seedlings is truly 3:1. So we can use a test of proportions for this. And so, as always, our first step is to write out our hypotheses. So first we have our null hypothesis. So in our null hypothesis, the true ratio of green to yellow will be 3:1. And so that means that we'll have, for our p, so we'll have our proportion p will be equal to 3 greens out of a total of yellow and green, so that's 4, since there's 3 green and 1 yellow, so that would be 0.75. And now we have our alternate hypothesis, and again, since we're just testing if it is the true ratio and not if it's greater than or less than, we use a two-tailed test, so that means that our p is not equal to 0.75. And then now we can look at the values that our problem gives us. So here's our sample size n, and then we have our ratio from green and yellow. So our ratio for green is our p hat, which is equal to 854 divided by 1103. And that is equal to 0.7743. And now we have all our values, so we can plug it into our z statistic, so we can calculate that. So we have our p hat, so that's 0.7743 minus our p-value 0.75, and then square root of 0.75 times 1 minus 0.75, and then all of this divided by our n, which is 1,103. And then if we calculate this, we should get our result, which is 1.8638. And so that's our z statistic. And now that we have our z statistic, we can again calculate our p-value, This is different from that p. We'll maybe call it p-value just so it's clearer. And this is, again, the probability that our null hypothesis is true, but we still got these values just by chance. And so that's, again, since it's a two-tailed test, we do 2 times the probability of z being greater than the absolute value of our test statistic, and we can look it up on the table again. So our test statistic is 1.8638. So now we can pull up our z table. And we'll see over here, so we have 1.8, and then 0.6 is over here. So if we look at the intersection, we get this value over here, 0.9686. But remember that since our table calculates the area to the left of our z-value, but what we want is this area to the right of our z-value, since we're looking for the tails. So we need to calculate 1 minus this value over here. So we have 1 minus 0.9686, and then that is equal to 0.0628, and this is greater than our alpha value, which again is 0.05. Forgot to write that earlier, but that's the alpha value that we always use if they don't give us an alpha value. And so since it's greater than our alpha value, we fail to reject our null hypothesis, and we can't accept it because we haven't proven that it's true, but we just don't have enough evidence to prove that it's not true, which is why we fail to reject. And that's this problem. And now for our next problem, we want to calculate a 95% confidence interval for the percent of US adults who regularly watch television shows through streaming. So since this one is a confidence interval, we can start with finding our alpha value. So our alpha value should be 1 minus our interval percent divided by 100. So we have 0.95. So that means our alpha value is 0.05. And then we have over here our sample size, so that's our n, and then we have our p-value. Our p-hat value is 43%, so that would be 0.43. And then I have our formula for our confidence interval for proportions over here, and we can just plug that in to get our values. So first we also need to find our z values, so z with our alpha here, so it's our alpha divided by 2, so that would be z with the alpha value of 0.025, and we can pull that up on our table. There we go. So we can look through these numbers, and Let's see where it is. There we go. So we have 0.025, and so our z value here is 1.96. If we use that, and then since our area under the curve is to the left of the curve, we're actually looking at this area back here. But since we want the right side of the curve, we can just make our value positive and then just have it be on the other side for our other tail. And that's 1.96. And now that we have our z value, we can calculate our confidence interval using our formula. So we have p hat, so 0.43 minus 1.96 square root of 0.43, 1 minus 0.43, and then divided by our n, so it's 2300. And then we have the same thing, except we want to add our values. And that's our confidence interval. And then that is equal to 0.4098 and 0.4502. And so now to interpret our confidence interval, we can say that we are 95% confident that the true proportion of U.S. adults who regularly watch television shows through streaming is between, and then these are our values again, 0.4098 and 0.4502. And that's our answer. Okay, finally, our last problem. So we have a manufacturer of washers, and we want to know if the customers prefer color A. And we want to use a hypothesis test for this. So the first thing we need to do is write our hypotheses. So we can say that for our null hypothesis, it'll be that customers don't prefer color A. So according to our problem, it says that customers prefer color A only if more than half prefer A over B and C. So we can say for our null hypothesis, our proportion is equal to halves. And then we can say for our alternate hypothesis that our proportion is greater than 0.5. So this is a one-tailed test, and it's very similar to a two-tailed test, just a couple of differences. So again, we can use our z-statistic, so I have that written off to the side, and let's first find our values. So this is our n, and our p-hat is 400 over 1,000, that's a 4, and that is equal to 0.4. And then now we can calculate our z-statistic. So we have z equals 0.4 minus 0.5 divided by the square root of 0.5 times 1 minus 0.5 divided by our n, which is 1,000. And all of this is in the square root. And if we solve this, we get our z value of negative 6.3246. And then now we can find our probability, our p-value. So that, since it's a one-tailed test, it's the probability of z being greater than our statistic. So it's the area under our z-curve that's to the right of our test statistic. And okay, and then we can look up our value on our z-table. So now that we have our z-table over here, we can find our value where our z is equal to negative 6.32, and we see that the lowest our value goes to is actually 3.4, and here is the area to the left of the curve. But since we're looking for our probability that z is greater than our test statistic, then we're looking for the value to the right of the curve. So our value should actually be 1 minus this value, so it's 1 minus 0.003, which is 0.9997, and then this is already a huge value, and this isn't even all the way to our negative 6.32. We definitely do not have enough evidence that our value, that our null hypothesis is not true, so since this is way larger than our alpha value, so here we have that our p-value is way greater than 0.997. I don't remember how many zeros it was. It was something around this. And that is way larger than our alpha value, which again is 0.05 when we don't know, when they don't specify it. And so since it's way larger, we fail to reject our null hypothesis. And so we have no evidence of preferring color A. And this also makes sense when we look at our values. Since we have 400 being sold, this is already way less than our 0.5, and so we obviously don't have enough evidence that it's greater than half, which is why our p-value is so large. So yeah, and then that is all our problems. Yeah, that's it. And if you have any questions, always feel free to stop by office hours. And good luck on your homeworks and exams and quizzes and whatnot. Bye, guys.